Hello, everyone. Welcome to the session on uncertainty and calibration. My name is Razieh and Nabi. I'll be chairing the session. So today's session, we have 3 talks, with the 4th talk, as mentioned, is already recorded and available online for your review. So without further ado, let's start with our first speaker, Siyu Mingyu, talking about the price of valid inference after causal discovery.
Okay, thank you very much for coming. After lunch, right? I hope my talk will not make you sleep. Okay, I think that's important, all right? And, my slide contain a lot of mathematics, but I most likely will skip most of them so that you get the insight and the concept first, all right? Now, if you look at the title, this is a very big problem. The problem is about the causal discovery, right? Usually when we see a data set, let me give you a very simple example. Now, how many hours a student study and what the grade and the exam score he will get? Do you think they are related? Maybe yes, right? Maybe no. Now, so in fact, what we are trying to do is we are given a set of data set, and what we want to do is I want to know which variable actually directly affect the other variable, kind of like a cause and effect inference, okay? Now, this is a very big problem in many areas. Now, let me give you more examples. Another example is like people talking about, in the internet, you can find many examples, like if you drink coffee more, do you have high blood pressure? Okay, or if you got this DNA, are you going to get this disease directly? Or there are many examples, like I don't know what variables basically directly affect the other outcome or variables, right? Now, so this is basically the basic problem we are talking about. So what we want to do is I am given a data set, and there are many variables, okay? What I want to do is which variable is the cause and which variable is the outcome, whether they are directly related, okay? Now, this, why I want to talk about this, because we are talking about uncertainty here, right? Okay, now, this is in the top row, you can see that we have a standard procedure. In fact, this standard procedure has been used in all areas, even like disease detection, things like that. Now, let me just go through the standard procedure first, all right? Now, the standard procedure is very simple. I give you all the observed data. So data Y is basically the observable data, okay? And then what I'm going to do is I will make use of some standard algorithm. In fact, there are many of them. I named 2 of them. One is FCI, the other is GES. In fact, the most basic one is FC. I will talk about that later, okay? Now, what we want to do is I want to check the variable value. For example, variable X and variable Y. I want to check all the observed value, whether they are correlated. Now, if they are correlated, I create a graph, okay? And this graph, the node will be the variables. And if X cause Y to happen, then I put an arrow there. You understand my point? All right, very simple. So basically, after discovery steps, we are going to have the graph. Usually we call them PAG or CP, DAG, it doesn't really matter. Okay, but then after you create a graph, some of the path may be wrong, and some of the variables may not be discovered because they are hidden. Okay, now let me give you one example. Now, if I only record how many people eat ice cream today, and how many people go to swimming today, then you may think that, oh, they are correlated because, the number of people who want to ice cream is correlated to the number of people who want to go to swimming, right? But basically, the hidden variable is not these 2. It's because the weather is hot. You understand my point? So basically then, finally, after we got the path, we check every path and see which path is reasonable and which path is not reasonable, and put in additional variables. So that's the last box over there is the adjustment set, okay? In order to make sure that some paths are not valid, some paths are valid. Now, I don't want to get into the detail, but the concept is kind of like, I look at the data set, I create a graph, and then if the variable connected together are correlated, I put an arrow there, then got a graph, okay? And then finally, after we got this graph, then I'm trying to tell, okay, this variable x and variable y, how much they are related. So if I set the confidence level to be 95%, then if it's based on the data, I will check it using statistics, okay? If it's not 95%, I remove the edge, okay? Then finally, I should be able to get a graph so that the cause is x, then it will induce y, maybe y induce z, okay? And all this edge has 95% confidence interval. So everybody here, this is what we are going to do using observed data set to deduce the observed cause and the final outcome. Now the problem is, I highlight in red. You think about it, I use the same data set to construct the graph, and the same data set to induce the confidence level. So basically, that may be a problem, right? Okay, now, so the final result, we did some experiment on the, let me see. You see, we do some experiments with some real data here. Then you can see that sometimes, even we set the confidence interval to be 95%, but in reality, the situation only occur in 72 to 82%. So basically, some of the, the inference, like, oh, the cause is X, but the outcome is right, may be wrong, okay? Now, so this is the problem that we are going to resolve today, all right? All right, now what is the missing part, okay? The first one is, I think there are many terms, I don't know everybody in the room, if you're in the area, basically it's some basics, right? But if you're not in the area, maybe you don't understand. Let me just explain them one by one. Now, there are three problems we have here. Now, I told you an example already, right? If you only collect the data, how many people eat ice cream, and how many people who go to swim. Then if you look at the correlation, you will think that, oh yes, they are correlated. So the number of people who eat ice cream actually induce the number of people who want to go to swimming. But in fact, this is not the real fact, right? The real fact is the weather is hot, okay? Now, so basically FCI is the algorithm that will try to take out these hidden variables, even you do not collect the data from the data set, okay? But the problem of this one is, now then, FCI basically, I don't want to explain it because I only have 15 minutes. So if you really want to understand it, you go to my poster and then we talk, okay? Otherwise, you can read the, the detail of the algorithm. But in any way, what FCI want to do is to find out all those hidden variables that basically not X induce Y. Basically is we do have a set variables that basically induce the number of people who want to eat ice cream and induce the number of people who want to do swimming or something like that, all right? Now, so basically, but the problem is you can see that the search space is large. And then nobody tried to restrict the search space for the later steps. So basically, this is what we want to solve. So how you use the FCI result with more hidden variable comes in, but you still can confine the search space, like the threshold, how you set the threshold, in order to create a valid graph, all right? Now, the second one is GES. If you are in this area, you know GES is a score-based algorithm who try to think about it. I give you a set of data. There will be multiple graphs that will be produced, right? Maybe X induced Y is also correlated. It seems like Z also produced Y, but which one is correct? So GES is basically a score-based algorithm to decide which graph is the best in order to tell people which are the cause, which are the outcome, all right? And usually what the existing program is doing is because there are multiple graph possibilities, right? So they do randomization, okay, in order to do multiple steps in order to find the one that fit the situations, okay? But this is not a good way to do it. And the last part is the problem I mentioned about, right? You use the same data set to create a graph and the same data set to do the inference. Now, it's not correct, right? Just like you're using the same set of data to construct the graph and tell you the reason, okay? So the right way to do it is you should split the data. It's a very natural idea, right? You split the data, maybe it's part of it used to construct the graph, and then the remaining one used to do the inference, right? But the point is, then you use less data to create a graph, okay? And then less data to do the inference, then what will be the problem of the result, all right? So I'm going to talk about that. All right, now these are the, the mathematical stuff. I guess we just had lunch, right? I don't think you want to look at all the formulas, and let me explain all the variables. But, the biggest conclusion is here, okay? Now, usually in this kind of problem, what you are going to do is, I will set a threshold. For example, if X and Y, I check the correlation. If the correlation is bigger than 0.6, now 0.6 is important, right? Why 0.6, okay? Then I say that X will induce Y. So basically, finally, we want to get this kind of formula, we want to get a set of inequalities so that the variables together, they are connected in the inequality. If you think about it very carefully, it becomes a geometry figures. Like the space is like a three-dimensional space, right? And then if you, for every two variables, then you are going to get an inequality. Then actually you can try to group a region together. And this region basically is what we want, okay? Now, so if you want to know more mathematics, how we formulate it in mathematical form, I guess you can read our paper or go to the poster to look at it, all right? Now, let me summarize our contributions. Now, if you look at it carefully, I talk about the PC and the PCI, right? Now, PC basically assume that all the hidden variables are basically in the data set, but everybody knows that is wrong, right? When you measure the data set, you always miss some of the hidden variable. And PCI basically is the one who will take out the hidden variables in order to connect the variables together, all right? Now, and GES basically sometimes we need to do randomizations. I talk about it already because there are multiple graphs that appears, right? Now, so in our work, we basically focus on FCI and GES. Now, FCI, the main advantage is they will take out the hidden variables. Instead of assume like PC, all the hidden variables exist already. Everybody knows that the assumption is not correct, okay? And GES, we will show that actually GES, we might not need to do randomization. We can actually do it in a faster manner. Now, I think the key point right now is nobody in the area try to think about how to make PCI and GES results more reasonable in order for the following step to do the inference. Okay, basically we are doing something like this. And latent cofinders basically are the hidden variables. Then you can see that all these previous work didn't consider it except us. And a truncation set, I want to explain a little bit more on this truncation set. Now, truncation set is very important. It's basically, we got all the data, right? And then we got the graph and connect them together with the cause and the outcome. But the point is, some of them are wrong, some of them are correct. Okay, now how you set the threshold? Then if you set the threshold, basically if you imagine a three-dimensional space, then we set the threshold, it becomes a polygon. Okay, and basically that's the transaction set. I think in the previous work, they never consider how we can get this constraint from the PCI and GES earlier so that we can confine the space, so that we can know that, oh, which the factor will be the cause, which factor will be the outcome. I guess this is our main contribution there. And of course, the other one is like, for example, coverage means that if the data set actually satisfies one condition, then we got a more exact interval. In other words, if you're talking about 55% confidence interval, then we can apply this result to around 95 real cases instead of the problem I talked about. Now, the problem I talked about is like, even you say that I want 95% confidence interval, this X actually causes this Y, but in reality, the situation is not the case. All right, sometimes it only be real for like 70-something%, okay? So that's why we do something like this. And the last part is we talk about we split the data set into two parts, one to construct the graph, the other to do the inference, and we are not God, right, okay? So basically, we still have some constraint. We make the interval maybe a little bit wider, larger. So it's not only 72 to 82, maybe 80 to 95. But we have a more accurate interval, saying that in this interval, our result will be more reliable, all right? And the cost of it, and we do some experiments with a large data set like D equal to 200. I think the previous work, they only do like the number of variables up to 100 only, all right? I guess I prepared too many slides. Okay, I thought I have an hour to talk about it, but only I have 1 minute, right? Okay, so I will skip the mathematics. Do I have an hour to talk? If not, anyway, let me just tell you some of the, the experimental result. Let me see. Okay, now then you can see that. This is basically our experimental result using the real data. And we are the only one, you can see that we actually increased the number of variables to 200s, and the number of records like here, and then the accuracy is basically much better than the others. All right? So maybe I stop here first, and then see anybody have any questions. Thank you. I hope I can have an hour to talk about it, right? We haven't talked about the mathematics.
A good thing the poster session is 2 hours long. So let's take a couple of questions. Are there any questions for the speaker? One at the back.
Sorry, I don't think I understood the method. Was the final proposal that you do a split of the data with n to the 3/4?
Oh, you are talking about the method, right? The detail method?
Yeah.
Okay, now basically what we do is after the FCI, we do not disturb the FCI and GES to run their own algorithms. But then after running the algorithms, we check the result of the experiment and let's see whether we can set up an inequality to restrict the region. So that's why we can do a more accurate estimation on that. I guess the other approach is like either they don't consider hidden variables or they do not do this kind of truncation set. So the truncation set, the setting of the truncation set is the key. Why we do it so earlier? Because, once you finish one experiment, then I set one equation, you finish another test, then I set another equation, then you can see that even the whole space is large, but then we can restrict the region to be much, much smaller at the very beginning, all right? I hope I answer your questions. But, mathematically, you need to look at the paper, how we formulate this into a polyhedron, and then how we set up the inequalities, all right?
Maybe there's time for one quick question. Are there any questions? No?
They're looking for coffee time.
Yeah, that sounds good.
Okay,
So
thank you very much.
Thank
I
you.
will be in the poster section as well. So if you want to talk more, welcome.
Sounds great. Let's
Thank
go
you.
on. You're the second speaker, right? Yeah. Okay, great. So our second speaker is Minghao Li. And he's going to talk about label-wise uncertainty decomposition for multi-label classification by maximizing type 2 likelihood. Let's welcome our speaker.
Hi everyone. There are many people today. I'm a little bit excited and a little bit nervous today. Today, the title is Label-wise uncertainty decomposition for multi-label classification for maximizing type 2 likelihood. I will give some example to tell what is multi-label classification. Multi-label classification means each label could be the ground truth. It's different from the categorical distribution. So for example, the first picture, the person, the motorcycle, the car, they are all the ground truth. But from uncertainty people to say here, the annotation here, we think it is not deterministic. It's not just 0 or 1. And the uncertainty people will say, the Bayesian people will say the car here has a strong motion blur, and we think the probability could be like.
Could you please just adjust the microphone?
Yeah, okay.
There are slides here too.
Okay. The car here could, the ground truth, the optimal theoretical ground truth could be 0.9, 0.8. And for the right side, the picture there, the guy is holding a dog. And the annotation here, the ground truth is only the dog. They didn't annotate the guy as the ground truth, but we can see the part of the guy. So Bayesian people, as a Bayesian people, we think there's uncertainty for the guy here. And the traditional method for to discover the uncertainty here, we may to learn the probability and use the probability to learn its uncertainty. But now, in our paper, we are arguing the probability P may not be expressive enough to tell all the uncertainty information. So here's an example to say is for the traditional method, we use the neural network to learn likelihood. For the multi-label classification, we learn each label as a binomial distribution likelihood. Then we learn the probability P. This P is not following the restriction of the categorical distribution. It will be like whatever 80, each label could be 80, it do not have to sum to 1. And we learn the probability P. We may calculate the entropy to find its uncertainty. But now, as we can see, the entropy here is only controlled by the probability P. And we think the probability P is not informative. So we argue what if we learn a better distribution with the parameter A and B? And we can see on the left side, the P, for all those different beta distribution has the same probability, 0.5, but they have totally different shapes, and they only use the probability p. We cannot learn those informations. And if for each label the uncertainty is following a beta distribution, and we can see on the right side, it is not just a simple one-dimension information. This is controlled by two parameters, and we can see informative uncertainty information. Like entropy is like one-dimensional uncertainty information, and for the beta, we will see a two-dimensional uncertainty information. And traditional method, we will use the binary cross entropy. We build a type 1 likelihood for each label, then it will be a binomial distribution. Then we put the negative log on the likelihood. We can learn the probability p. And now we learn a type 2 likelihood. The type 2 likelihood on the left side, the py given mu is the binomial distribution, same as the type 1 likelihood. On the right side, the p mu given a and b is we can, from Bayesian perspective, we can treat it as a non-informative pry. We don't want to add too much information. It's a non-informative pry. And we integrate the mu out to learn the py given a and b. And for this method is not a new method. This learning method is like 30 years ago, the Bayesian people proposed. They call it evidential approximation, or they call it, or people also call this empirical base. So we put the negative log on the second order likelihood. Then we can have a method is maximizing the type 2 likelihood. Then another method is called Gibbs classifier. The difference is about the integration. In Gibbs classifier, it will integrate the mu with the negative log of the first order distribution. The negative log, the convex function will make this different from the type 2 likelihood. And we use the Taylor expansion to show the Gibbs classifier. It is actually equal to the type 2 loss as a variance, a second order variance related term. It's kind of restriction, regularization for this learning target. It's about the variance of the mu. And our experiment showed the type 2 likelihood actually achieve a superior results compared to the binary cross entropy loss and the Gibbs classifier. Gibbs classifier here, it have a pretty poor performance, but we can understand it because it is like has some regularization. Maybe it can work better for other datasets. So from the architecture perspective, we can see in our model is on the right side. In the outputs of the neural network, we have 2 times outputs than the normal method. We have normal method, we only need to learn the p of the each label. And for our method, we need to learn, for each label, we have to learn 2 parameters, a and b, for the beta distribution. So then we make a uncertainty decomposition here. The decomposition, mainly we assume the learning target T is following the predictive mu, and the predictive mu is controlled by the A and B. And we try to connect it with the Bayesian optimal, theoretical optimal mu. And here I mark it as mu star. And by adding this and minus this up, and in the end, the total uncertainty will decompose to the first order model variance, second order model variance, and the model bias and optimal spread. And first order variance is the expectation of the variance of the learning target T. Or we can call this in-group variance, because if we separate the samples to different groups, this first we get the variance first, then we take an expectation of all the groups is the variance of each group inside. And the second order model variance is, we can also call it outer group variance. It's like for each group, we take the mean of each group, then we take the variance of all the mean. And the model bias tells the difference between the optimal mu is the probability, optimal probability, and the predictive probability. And the optimal spread means the variance of the optimal mu. Of course, about the optimal mu, we cannot achieve it. This is just all we can do is by the observation from the model is about mu-related method. And in our experiment, we will mainly use the auto group variance, which is the second-order model variance. So here are some examples, like to say our models can tell the information which only use the mu cannot tell. For example, the car here, the model, the ground truth is the car, motorbike, and the person. And the model will give very low probability. If we only following the probability parameter, people will say, okay, I'm very sure there's no car here. But from a better perspective, we will see, even though it has very low probability, but its variance could be very high. And the green bar is the variance. And the second one is the dog. The model is saying there's a dog, but there's no person. But from a better perspective, is saying I'm very uncertain about the prediction of the class person, even though I have very low probability over the person. And there are a bunch of those examples here. Just a quick example, like on the right side, the fourth, there's a bus here. The ground truth is only the bus, but if we check more details, there are persons inside, there are people inside, and we can see the probability is 0. So the normal method will say, okay, I'm very sure there's no people here, but from a second order distribution, we can observe, even though the probability is almost 0, but we can still find its very high variance here. And we also use our method for auto distribution. I won't see too much math details, and we can see for the FPR 95, control the true positive rate, and we test the false positive rate. We improve the other multi-level auto distribution method, like 5%, 6%. And we also have many observations for those related work. First is, since we build a second-order learner, in a Bayesian, traditional Bayesian way, there's a thing is called sequential Bayesian update row, and it's like we flipping the coins. We can count how many times we flip. But will this Bayesian updating row work in a second-order model by the neural network? Can it behave like this? And our answer is yes, it will following a Bayesian update row. We just give a simple, brief observation here. And the second is we also find the neural network prediction predict the beta distribution. It prefer a U-shaped beta. U-shaped beta means the A and B all below than the 1. Because previously the evidential people, they prefer let the A and B higher than 1, but if we let the freely choose, they prefer the U-shaped beta. Okay, that's all.
Great. Any questions for the speaker? There's one question in the middle center.
Hey, thank you for the talk. Could you please maybe comment on the relation between these and, let's say, in the regression case, in the continuous variable case, just outputting the mean and the variance of a Gaussian or something like this and training for maximum?
This is the classification work.
Yes, but I want to know the relationship between
To the regression?
classification. Yes, would it be, let's say, equivalent? This is more or less what I'm thinking about.
I also did some work is about the evidential deep learning for the regressive work, and for that work is the experiment is not good as I expected, and that is I think for to build a Gaussian and for each Gaussian is for the more higher order is I think is more complicated than this beta. Yeah.
But would you say that this is more or less equivalent, like because you're
Yeah,
getting
they are equivalent or achieve a second order, a higher order distribution. But I think for the regressive work, it will be more complicated than this because I did many experiments. It's kind of the variance is not behave very stable, so I didn't continue for the regressive. Yes.
Thank you.
Are there other questions? There was a question on the other side. No. So maybe your question. Oh, you didn't have. Sorry.
Thank you. Is it possible to quantify something like a covariance for this? Because I think until now it's all per class, right? Or per.
Yeah. In this work, we didn't do the covariance check for the covariance for the multi-class. We just consider each class as an independent class.
Yeah.
So we didn't test the covariance information.
But do you have an idea whether it would be possible somehow?
For the correlation between the classes, I think my thinking is the neural network will organize it like all the parameters is all the relationship will reflect in the black box. Maybe like the dog and the person it has more high probability be together in the ground truth, but those information is hidden in the neural network. So we didn't do any other learning target to specific to set for those information.
Okay, thank you.
Yeah.
Questions? There are two at the back. So maybe the first one. Yeah.
Thank you for the presentation. Maybe a follow-up question from the last one. I see that you use beta distribution, like independent beta distributions for the outputs, right, for each class.
Yeah.
And normally in classification we have multinuclear distributions, right? Like we have class probabilities adding up to 1. So why don't you consider using a Dirichlet distribution instead?
The Dirichlet is the higher order distribution of the categorical distribution, and that is for multi-class classification. And in this task, we mentioned in the title is multi-label classification, which means each label all could be the ground truth, all could be true. In multi-class classification means only one class could be true. If you find this is the ground truth, then you can deny rest of them. So they are following different distributions. And
okay.
also if you use Dirichlet, the outputs numbers will be same as the class numbers. But our use this method, the outputs will be 2 times more outputs from the neural network than the normal method.
Okay, thank you very much.
Thank you for your talk. Question, have you considered the fact that more data doesn't imply that you have more certainty on the predicted uncertainty?
It's like the observation here. We try to increase the size of the data set, and we can observe the beta parameter A plus B will growing. And this growing is what I mentioned, like in traditional method, there's a sequential Bayesian update row we think this is kind of following the Bayesian update rule, and this Bayesian update rule means it is become more certain.
And do you have any theoretical result for the Gibbs loss function you have used for training, or is just tested empirically?
You mean the Gibbs classifier?
Yeah.
Gibbs classifier, I didn't test it. I only test the performance here.
Okay.
The performance is like here you can see is 0.78 on the ResNet 34 and 0.82. For the Gibbs classifier, my advice is it doesn't behave very stable. Maybe the regularization here is too strong, but it can work well because I also have other works is about related work, and it can achieve a pretty good result, but not here in this task.
Okay, thank you. I had more questions, but probably we take it offline. Thank you.
You're welcome.
Great. Thank you. So we move on to the last talk of the session.
Thank you.
Our last speaker is Chengfeng Huang, and he will be talking about model-agnostic online certificate-driven calibration for time series forecasting under distribution shift.
Okay. Hello, everyone. I'm Chengfeng Huang from UCLA Statistics and Data Science Department. Here today, I'm presenting our paper, Model-Agnostic Online Certificate-Driven Calibration for Time Series Under Distribution Shift. A reliable forecasting under distribution shift requires forecaster to remain reliable when deploying dynamic differs from training condition due to 3 challenges. The first will be the covariate shift. So its input marginal distribution involves while conditional predicted distribution remain invariant. For example, it could be elicited by the sensor replacement or changing the operating conditions. And the second will be the concept shift, which will be the inverse way that conditional distribution changes while input marginal distribution remains stable. And it corresponds to fundamental shift in data generating mechanism could caused by the factor like regiment shift or involving dynamic changes. And also temporal dependence. The time series observations are sequentially dependent. So meaning that the current and future values are influenced by past observations, trends, seasonalities, and lag effects. This could cause old degeneration harder because shifts can propagate over time and cause a cumulative forecasting error. So our goal is to perform online calibration with approvable reliability. So let me explain what is online calibration and how it works. So first, we capture the backbone prediction and we calibrate based on the predict. Then which avoids the data leakage to strictly follow the Coyle order in reality that we can only access the ground truth after prediction being made. So this animation visualization here also showing we firstly have the dashed blue line, which is the backbone prediction. Then our calibration gonna calibrate based on that predict, and we have the ground truth updated. However, we found the existing online calibration framework are insufficient. The solid, its performance depends on retrieving relevant context. However, repeatedly fine-tuning might be unstable under noisy or sudden shifts. OneNet, its assembly improves strict tracking by introducing additional model and update overhead with limited protection against harmful adaptation. And Proceed, its adaptation relies on a learned drift representation which may not transfer when deploying shifts differ substantially from training observations. So these findings motivate us to propose a certificate-driven online calibration for time series. So such certificate should suffice 3 challenges. It should address temporal dependence, and it should detect shifts before label arrives to follow the Coyle order in reality, and it should regularize the online update to avoid overly aggressive online calibration. So the pack-base becomes an appealing candidate. It separates the source risk, complexity, the source target mismatch, which naturally becomes an optimization object for conservative adaptation. In the following slides, I will elaborate details of the 2 essential components of pack-based bounds, the complexity and mismatch term. The complexity term consists of a KL divergence between posterior and prior distribution, a confidence penalty, and a sample size scaling term. The certificate means with a probability at least 1 minus confidence parameter delta, the true risk of randomized predictor is bounded by its empirical risk on the training sample plus a complexity penalty. And this penalty increases when posterior moves farther from the prior and decreases as the same sample size grows. And the bound therefore balances the training fit against model complexity. However, it assumes the training data are drawn independently from the same distribution as evaluate target domain. So under the classical setting, the IID assumption failed under the context of time series. We therefore leverage a martingale concentration with sub-gamma assumption to construct a dependence-aware pack-based certificate by replacing pack-based complexity term with sub-gamma martingale term. And let me define the PB as a complexity component of a classical pack-based bound without the sample scaling term. The martingale concentration yields a variance-adaptive pack-based penalty. The complexity PB is scaled by the posterior average cumulative conditional variance V sub gamma and tail scale C bar, while decreasing as sample size grows. The sub gamma assumption limits the magnitude and frequency of unexpected forecasting error shock, enabling reliable risk bounds under temporal dependence. And the mismatch term is calculated from the predictors from the posterior and examine how spread out their forecasts are. So we compare the average posterior spread on source replay windows with the spread on the target window. Since the mismatch is computed between two posterior predictors, while the risk is defined for one predictor, so the pairwise disagreement contributes 1/2 of single predictor risk. So we have this 1/2 coefficient in front of the mismatch term. And finally, we have a certificate for source risk that keeps the calibration close to the reliable source behavior. And we have a martingale correction that accounts for temporal dependence, posterior complexity, and changing loss scale. And a mismatch that increases with posterior forecast disagree more on target window than on source window. So together, we construct an interpretable online calibration certificate for monitoring distribution shift and regularizing calibration. And now let me introduce our major contributions, the online martingale pack-based framework with abbreviation OMPB. It includes the following essential components: a frozen backbone, which preserves the forecasting knowledge, and lightweight residual Bayesian head, which provides a tractable complex pack-based penalty with a gating mechanism, which is a safe fallback to the backbone when it shows uncertain. And we have also a certificate that regularizes updates to avoid overfitting on target label. The overall pipeline has 2 stages. The offline stage, we train the backbone and initialize our Bayesian head. And during the online stage, we make the prediction, compute the certificate, and update Bayesian head given the revealed target label. In the experiment, we attempt to answer the following questions. Does OMPB improve the OOD forecasting? Therefore, we test the covariance shift using energy field data sets ETTH, where ETTH2 and ETTH1 use the same hourly forecasting schema and variables, but they were collected from 2 different locations under different operating conditions. Consequently, the input window can have different low-level temperature ranges, seasonal patterns, and margin distributions, which is a typical case of a covariance shift. And for the concept shift scenario, we use medical data set ILI. In the ILI data sets, the pandemic disease transmission, intervention, and healthcare behavior. So the relation between recent illness history and future outcome are fundamentally changed, which presents a concept shift. And also we further testify our framework on the covariance shift with increasing spatial shift severity as the distance from Miami increased from Atlanta to New York City. Then we testify whether our framework is model-agnostic by testing it with representative time series forecasting backbone in convolutional network, TCN, and the transformer-based approach, Autoformer, and latest large language model approach, GPT-4TS. And finally, we performed the ablation study to verify the effectiveness of our gating mechanism, the pack-based penalty, and the online calibration schema. The results of ETTH and ILI verify the OMPB framework effectiveness under both covariate and concept shift. The framework improves performance in both in distribution and out of distribution. In more significant concept shifts, the OOD improvement is more explicit compared with in-distribution performance because backbone performance under such OOD scenario is much worse, which potentially leaves more room for improvement. And also among all the baseline, whereas only framework has no negative effect in the in-distribution performance. And in the weather data sets, the OMPB also shows consistent largest improvement among all baseline. In case of covariance shift with increasing spatial severity, our approach shows larger gain under further OOD shifting as percentage of improvement is largest in the New York City testing set. It reflects the robustness of OMPB against increasingly different target domain from source domain. And we further verify how certificate behave to verify how it works exactly. The upper panel plots the value of the source risks, the martingale pack-based penalty, and also the mismatch term, and in addition with the IID pack-based term, the red line there. So you will find out that IID pack-based complexity seems looser than the martingale one. Well, that does not imply every martingale bound is tighter than the IID bound. Here, the game comes from the martingale variance adaptive correction when loss has low predictive variation. And the middle panel measures the distribution severity for four classical measurements, KS distance, the Wasserstein, the JS divergence, and radial basis function maximum mean discrepancies. And lower panel shows that realized target error that is uncalibrated prediction error. So all of them together shows a similar pattern, so we testify our certificate is not merely a heuristic regularizar but interpretable bound on target risk that responds to distribution shift correspondingly. And also in our main experiment, we assume the delay feedback of our target label is one time step, which could be optimistic in real-world scenarios since we're not able to get a ground truth immediately after prediction being made. So we test our framework with a longer delay in half window size and a full window size and even a double window size. And under the context of TCN as a backbone, the OOD performance of double window size delay is still better than the pure backbone prediction. And also there's a visualization of the different delay feedback in terms of the time step, each time step's arrow for the 500 time steps. And besides, we further address the concern of the expressivity of a Bayesian layer by introducing more trainable parameters by unfreezing the last layer and or the LoRa-style online update. They both degrade the performance in MAE and MSE, suggesting that extra online flexibility can be harmful under delay supervision context. And, okay. We perform the three kinds of ablations. We remove the gating mechanism to verify the no-harm effect, and we remove the pack-based term to verify its effectiveness. And then we disable the online calibration to enforce the framework as an offline learned Bayesian layer. The online calibration is a MERN performance driver, which is expected. For example, because the offline training case, it can only access the ETTH, which is a source domain. So the resulting pack-based certificate cannot account for the ETTH2 shifting. So only during the online stage with ETTH2, the target label being revealed, the OMPB can estimate a countable certificate between source and target domain. And the pack-based term performs a role of stabilizing the calibration. And the gating mechanism is more interesting. So the gating mechanism shows the benefits on ETTH and weather data sets whose sample size is way much larger, while it shows negative impacts on IOI data sets whose sample is only like the 100, while the others are like the more than 10 times more. So this kind of implies with limited samples, more aggressive calibration may yield better performance. So in summary, our major contribution can be summarized as the following. The OMPB is the first martingale pack-based online calibration framework for time series OOD generalization, and whose certificates remains valid under temporal dependence. And it shows consistent gains across TCN, autoformer, GPT-4TS under both covariant and concept sheet. Thank you.
Any questions for the speaker? One at the back.
Hello. Thank you for the presentation. In your opinion, is MAE, MSE still the best choice of loss for time series dataset?
Depends on what task you're trying to achieve, like forecasting.
Yes, especially for forecasting.
Well, it's a little bit different for our case, but in general, it's a definitely important choice. But in this context, we are not really training the backbone. We are training like the additional Bayesian layer, which is our main contribution. So in that case, MSE solely alone might not be sufficient.
I see. Okay, thank you.
There was another question around the same corner.
Yeah. Thank you very much for the presentation. I want to ask for a bit more insight on the derivation of the bound that you gave, if possible, because it seemed like it was derived from a classical relaxation of Marer's bound, maybe the one coming from the Pinsker inequality. And there are, I think, stronger bounds that maybe are less mathematically tractable. So I wanted to ask if you've considered them, and maybe some insight on how you came to that formula to see if you could make a similar derivation from a stronger bound.
Yes. So this is actually a little bit mentioned in the, I forgot where, just like application study somewhere. But anyway, so the PAC base is very suitable for the online calibration, not under classical supervision context, because only in the online calibration case, your access have for the both target domain and source domain. So in the classical supervision context, you only can generate the PAC-based bound for the a source domain, which may not be beneficial for your OOD generalization. But in this specific context of online calibration, it works very well. So of course, if you're referring some other less interpretable bounds, that might also work, but the PAC base under such kind of a context, and it can be applicable, so it gives it its additional edge. So that's a part of the reason I choose a PAC base here.
Oh, I'm sorry if I'm allowed the follow-up. I was referring specifically to PAC base, but there are stronger PAC base bounds as well.
Oh, okay. Oh, yeah. So this one, the classical PAC base has IID assumption, right? So we're trying to consider that kind of restrictions. If you're like the tighter bounds, also consider that case.
Yeah. If it's okay, I'll approach you offline.
Okay, sure. Okay.
Thank you. Other questions? Yes. Just bringing the mic to you.
Does it work now? Yeah. Okay, thank you for the talk. I also have a question regarding the bound, because you have this disagreement term on the right-hand sound that upper bounds the risk of the target, and this is the disagreement between source and target, and I was wondering, like, what kind of, maybe I missed this, what kind of assumptions do you impose? Because hypothetically speaking, in a time series context, source and target could be completely unrelatable, and then this is like totally vacuous, and I was wondering with what kind of assumptions you work here, because you somehow have to restrict the drift, I suppose.
I think we don't need to really restrict it. We need to make use of it. So because if you solely only have that source domain data, the certificate may not really contain that kind of shift information. So the mismatch term is a perfect a capacity that to capture that information into the surrogate update.
Yeah, maybe the question was not perfectly aligned. It's more about...
I mean, additional assumption about it?
Yeah, I mean, I understand. So you use the source data to inform the target, but then still, like, what do you do if the target is completely ill-aligned with the source, for example? I mean, then I guess the bound becomes very, very large.
Oh, yes.
And then but this has to happen naturally. This was more the question.
Oh, yeah. There are some more technical details in the poster I will show by a cut of this. There's a scaling term. Actually, I will there's a scaling term tau that I will use solely on the training data to find the relatively appropriate one to restrict that mismatch term within 0 and 1. So yeah, it's kind of omitted here, and there are more technical details we can discuss in poster section.
Thank you.
Maybe a quick follow-up. Does having a better certificate always imply a better forecasting performance?
Well, not quietly, since this more technically is like the spec-based motivate surrogate. So it's not like really we're not trying to upper bound the MAE and MSE here. So its behavior is showing like it has a pattern corresponding to a distribution sheet, but trying to really minimize it, at least it works for the Bayesian layer. But if you're trying to apply some different things, probably we need more empirical result for it.
All right,
yeah.
Thank you. Are there any other questions? No? Okay, great. Let's thank all our speakers for this session.